Thank you. So I'm Pengjie Wang from University of Illinois, and I really hope that I could be there in person, but due to all the visa and uncertainties that I cannot be there. So today I'm great that I can still give the talk remotely, and so I will mostly focus on the anisotropic Moire system. So as you mostly has heard about during the workshop this week, and the focus is mostly on the TMD system as well as the graphene system, which mostly comes with the system you have the triangular lattice. And in today's talk that I want to introduce is another unique Moire system, which is going to give you some anisotropic features, and those can also give us interesting quantum phenomena. And so to begin with, I want to give you a quick overview. So as you might all know about the Fermi liquid theory, which has been a standard description for metals in 2 dimensions and 3 dimensions. And it can help us to very well understand or very well capture the fundamentals of the quantum Hall effects as well as the superconductivity, which has been dominating the condensed matter for long decades. And another category which we actually rarely known, and it could be the system which we cannot understand by the conventional Fermi liquid theory, and because it's like a fish in an ocean that we don't know, and so like we and then we mine them, then oh, they are non-fish. And like taking the same category, then we take the Fermi liquid theory, we call them non-Fermi liquids. So which is the behavior out of the comfort zone by the Fermi liquid theory. And with this, we have heard a numbers of behavior. For example, the famous strange metal behavior, which indicate the resistivity versus the temperature is the linear relationship rather than the Fermi liquid power law. And my colleague Philip Phillips as well as Peter Momonti, they have a wonderful summary for many systems which shows up a strange metals behavior. And this actually has categorized numbers of systems which didn't show the Fermi liquid theory behaviors. And another example is the Latinger liquids. So Latinger liquid is a one-dimensional system. It also goes beyond the Fermi liquid description in 2D and 3D. And as well as the fractional quantum Hall effect, and you might heard about recently the fractional quantum anomalous Hall effect, which is also in this category. So one funny issue, I put this figure here, but one interesting phenomenon from the Fermi liquid is that you can treat the electron as a single electron in a cloud of electrons. But as an analogy for the non-Fermi liquids is that the electrons here are just strongly correlated. So I put a picture of GIF figures here, which is actually Brazilian football fans, and everyone collected, and when during the World Cup games, and so you can imagine that to such an analogy that the Fermi liquid is actually you just only need to renormalize the effective mass of an electron, and then we can use the single electron model to understand the electronic properties inside a solid state. But in the non-Fermi liquids, all the electrons are strongly correlated, and in this way we cannot really identify or we cannot distinguish electrons. We need to understand them by some collective correlated excitations. And so moving towards, so the direct results of such a strong is the fractionation. And such a fractionalization, as you might have heard, also as well as in such a workshop, then fractional charges has been proposed in many systems. For example, the very ancient fractional quantum Hall, and now there are also proposals in the fractional quantum anomalous Hall effects. And so people have been pushing extremely hard to understand how the fractional quantum Hall effects has such a fractional charges. And if you can cool down all the electrons down to an extremely low temperature, for example, 4 millikelvin electron temperature, people can see such an even denominator fractional quantum Hall state. And this state, they can further propose, people have further proposed it could be used for topological quantum computations. And such a one-quarter charges is an exotic phenomenon. Another interesting phenomenon comes out from fractionalization is the spin charge separation. So basically, you can analogize to a situation that the spin and the charge will effectively to be separated in the system. So today, what we have been talking about is mostly the 2D van der Waals systems in this workshop. And it's very easy to explain the system because we can just use a Scotch tape measure, and then we can use a microscope to visualize or directly observe such a single layer flake. We can also use the advanced method to image the layer structures. So with this, then we can also have a huge amount of tunability. For example, you can easily stack them. We can also create Moire, which everyone has heard about during this workshop. And we can also tune their density, the displacement field, and we can apply some magnetic field that both work, as well as we can apply pressure. We can use light, strain, and temperature magnetic field. We have a huge amount of tuning knob that we can tune the systems. And one thing that I want to highlight in this workshop, which is the Moire structures. And you heard about many stories about the flat band, as well as how we can create them down to the fractional quantum anomalous Hall effects. And in the Moire system, you have heard about superconductivity, you have heard about the correlated insulator, you have heard about Moire excitons, you have also heard about the quantum anomalous Hall effect, mechanism, quantum anomalous Hall effect, fractional quantum anomalous Hall effect, which has been all covered during this workshop. And the new system that I want to introduce today is the so-called Moire-Latinger decrease, which was done by the twisted bilayer tungsten ditelluride, and it's a unique system that you can give you the COSY 1D structure, which is the parallel conducting and non-conducting channel interchanging in the two-dimensional situation. So before that, I just want to say that in the two-dimensional system, actually we still have a huge amount of material which we haven't explored. And the situation which people have been studying is just a few dots on this table. So this plot is actually plots numbers of material which are categorized whether defined whether they are easy or not easy to exfoliate. So you can still see that there are more than 1,000 points or more than 1,000 material that are easily exfoliated in 2 dimensions. And we have a huge amount of opportunity to explore these systems. So to go back to the Fermi decrease theory, then the behavior or the spectrum of the energy in the momentum space is, you can simplify it as a parabola. It's like people loosely in the square. But in the non-Fermi decrease system, so one example is that the one-dimensional Latinger decrease. So the electrons are related in 1 dimension. It would be like when you went to a supermarket and then you are checking out, and people are waiting in a line, and even someone want to kick into the line or someone move forward or backward, is still going to interfere with other persons. And so this very weak interaction still can give you a strong correlations. And moving forward, this the momentum space spectrum is completely different from in these 2 cases. And one direct consequence comes with the one-dimensional interaction is that the energy or the density of state is suppressed by the power law. So this power law can be strongly related to the energy, and you can imagine that the strong correlation, one of them is the spin charge separation. So if you have the antiferromagnetic chain, and somehow you can have a way to remove one of the electrons from the spot, and effectively you can transport these holes toward to another side, which we can call it as a Holland. And then if this electron one by one, it will move forward to the right. And then what happens is that you will collectively have a spin which has the spin point down. And effectively, you can imagine that you have the spin motion and charge motion towards to the different position. So this is a simplified model that how to understand the spin charge separation in the systems. And moreover, the one-dimensional Lagrange liquid is solvable. So mathematically, there has been putting efforts in the around like 50 years ago, 60 years ago. People has been putting efforts in solving these one-dimensional Lagrange liquid systems. And there has been many examples, for example, nanowires, engineering quantum wires, topological quantum systems, as well as the Cauchy 1D structures in organic systems. So the direct result coming from here is that the energy is power law. So with the power law, you can imagine that either it could be the bias, so all the energy which we gave the system externally, or the environmental temperatures. So both should follow a single power law behavior. For this power law, you can, in carbon nanotube, people simplify it in such a equation, which you can imagine that it has a power law of temperature, as well as you can simplify this, the second term, as a power law of external bias. And mentally, if we just look into the system, so at a very low energy excitation range, then basically the temperature dependence should follow the power law on the conductivity. But at the very high energy excitation, the power law should follow with the external bias. In the past, there has been a discussion about whether we can expand the Lagrange liquid theory up to 2 dimensions or even higher dimensions. So can the Lagrange liquid behavior be stabilized in 2 dimensions, has been proposed by Phil Anderson to understand these behaviors. And the original purpose was to understand the Q-plate system, but later on, people actually expand this as a generalized theoretical platform. So for example, if you can pack the one-dimensional system and giving them a unique spacing, and with this spacing, you can create the intro interaction and also inter-wire interaction. And with this interaction, then we can do a quick analogy. Then at a very, very high energy excitation, the electron will be extremely excited, and then there will be no anisotropy. But with some well-suited temperature range, then basically the interaction between air and the intro-wire would be a little bit, would be something different. And with this energy scale, it would be very like the situation that I can see in the video, that everyone are sitting in the seat. And this is like each one are sitting in a row, and then we are correlated with within the row and intro the row of the workshop situation. And so if we turn the AC down much lower, I'm not sure whether the weather layer is extremely hot or not hot, but if we turn down AC in the room much lower, and then everyone will be freeze. So everyone doesn't want to move, and in such a situation, then we might go down to a crossover from the 1D to 2 dimension. And so one question is whether we can have a system that such a T crossover can be pushed down to extremely low temperature, or this is could this T star to just vanish at a very low temperature. So there has been numbers of proposals that such a system can construct a new phase, which is called symmetric metal or sliding Lagrange liquids. And in such a situation, that the strong correlation coming out from such a Cauchy one-dimensional structure can form a very strong anisotropy, as well as it should show the power law behavior when T approaching down to 0 temperature. And in this situation, even though you can view the system like a single one-dimensional wire in parallel to each other, but the system has a very strong interaction between the wire. So you can still find the interaction of the system, as well as if you want to reach to such a situation, you need to really fine-tuning the interactions. So this is a kind of, we call it as a 2-dimensional anisotropic Lagrange liquids. So experimentally, it's very hard to realize. This is just because with such a one-dimension 1D wires, it's really hard to control the distance. For example, if you imagine that we place the carbon nanotubes, and then we really need to put in efforts to make sure they are in parallel with each other and giving the spacing. But in Moire system, which actually can give us the crystalline quality as well as the high tunability. So I want to introduce this monolayer tungsten ditelluride, which you can see the latest structure in the lab. So the system has been studied for a long decade. This system was proposed and also observed with the quantum spin hole insulator, as well as the experimental study realized that it is a superconductor. So it's a tunable system that you can go to a topological phase as well as the superconductivity. And later on, our work revealed that it is possibly an external insulator in the monolayer quantum spin hole insulator. And the structure of this system is a rectangular lattice. So you can see that this such a rectangular lattice, it has a structure around on the unit cell to be around 1/2 along the short edge and also the long edge. And with this, you can see the zigzag chains, which comes from the tungsten and is forming in a 1D stripes. And with an STM collaboration with Professor Ali Astani's group during my postdoc, we can observe the cozy 1D channels on the monolayer tungsten ditelluride. We couldn't get the atomic resolution. This is mainly because we cover the sample with a simple nitride. And the sample is very air sensitive. So when we handle them, we have to do some spatial treatment to the system. So you can actually see here is that we are visualizing the up and down of the tellurium atoms on the single layer. And you can imagine that if we can do a twisting of such a material, then basically we can create such a cozy 1D structures with the 1D parallel systems. So this is the idea. So we create such a cozy 1D structures, and then we just twist them. And with the twist, we were able to see the moraines, which forms the rectangular lattice. So with such a rectangular lattice, if I remove all the tellurium atoms, so you can see that it forms a like cozy 1D structure. Overlap mostly here, mostly less overlap here, and then you can see the interchanging between this wire. So we call it AA with the most overlap region and less overlap region with the AB.
I'm not sure we can.
And you can also compute the distance just simply by all the Moire calculation. You can get the Moire distance of the systems.
Pengjie, I'm not sure we can see your cursor when you, or maybe it's just me. I don't know if there's something. Now I can see it. Yeah. Sorry.
Can you see it?
Yeah. Yes.
There could be some delay on the video, which I can saw it. I'll slow down a little bit.
Yeah. Okay. Yes.
So with this Moire, then you can basically seeing the structures, and is giving you the rectangle lattice. And with this rectangle lattice, we can even visualize the system. So this is a work which I had done in Princeton with colleagues, and we used a very simple nitride which covered the twisted tungsten ditelluride. And then with this, we can touching it down to the palladium metal, and then we can use a tip at room temperature to image the Moire system. So you can see here is the interchanging of the 1D structure, and even compute the distance between the wires. So if you compute here, this is a 5-degree twisting. Is in the measurement of the conductive AFM image is around 7.1 nanometer. So which is like very closely to the theoretical computation around 7.2 nanometer. So which actually shows us that there is almost no lattice reconstruction in such a system. So moreover, we confirm this with a TM study. You can see that the spacing with a 5-degree twisting, the system shows around like 7.3 nanometer in the spacing. So this actually very consistently showing that the Moire structure coming from it can give you a very nicely well-packed COSY 1D structures. So what I want to note here is that at UIUC with my students, we were able to develop another imaging method, which is called torsional force microscope, which was first introduced to the community by David Gordon's group. We were able to image graphene systems very easily by a typical AFM tip. We now don't need to introduce any electrode to the system. We can image the Moire of the system to image many Moire systems just by detecting the AC friction of the 2D. And this is a method so-called torsional force. And so to move forward, we are more interested in the collective behavior coming out from such a twisted system. So what we have been doing is that we do the transfer measurement. So to overcome the air sensitivity of the system, so we have to find some ways to carefully protect the sample. So which is very hard for us to do some etching or some typical fabrication method for 2D materials. Develop such point contact method, you can see that we particularly have the electrode exposed at the edge or at the tip of the electrodes, and which we can really contact the sample in the bulk of the twisted tungsten diterite. Another reason for using this method is because the tungsten diterite has a monolayer tungsten diterite has a topological edge mode, and so if you have all the electrode exposed, and then you are going to have a highly chance to touch the one-dimensional edge of the tungsten diterite. You are going to shorten the measurement, which can puzzle the measurements. So what we measure here is that we try to measure the devices along two orientations. You might heard about the angle dependence from Leo's talk. And so this is a very similar geometry as Leo's presentation. So we try to measure along different orientations of the measurements. And then you can see along two orthogonal orientation, we can see the resistance goes extremely high and goes extremely low. So along these two orientation, you can see that along one, we call it easy orientation, the resistance almost go to very low. But I want to note here, this is a scale problem, it's not a superconductivity. So if you check them in the log plot, you can see that along the so-called easy direction, or where the one-dimensional system parallels the transport direction, the resistivity or the resistance is on the scale of 1 kilo ohm. And then along the hard direction, which you need to transfer across the wire, you are getting the resistance on the scale of a few hundreds kilo ohms. And we can confirm this phenomenon by just simply doing the hard resistance over the easy resistance directions. And you can get the ratio of this anisotropy can go up to to around 1,000. And you can even get higher if you cool the sample down to much lower temperature. So we can further confirm this just by a dual gate tuning. You might have heard about the dual gate tuning to tune the density as well as the electrical field during this workshop. So basically you can imagine that on the left bottom side, here is where we have the most hole doping. On the right top side is where we have the most electron doping. And then crossing this tilted line is the displacement field directions. So you can see that it's barely the displacement field effect, but mostly the density effect. So if you tune the density along the charge neutrality towards the cold doping side, we see the huge anisotropy. But if you tune the density towards the electron doping side, we barely see the anisotropy. So it's a kind of tunable anisotropy in such a system. So with this, we can further confirm the transport property. We can dependence So with increasing the temperature, the anisotropy will drop. And along two orientation, you will see that along the hard direction, the resistance just keep dropping, and while along the easy direction, the resistance barely don't change too much. It will be mostly maintained at around like 1 to 2 kilo ohm. So along these two, you can see that the anisotropy mostly comes from the enhancement of the resistance along the hard direction. So we park the gate, so you can imagine that we fix the condition and as well as the displacement field into one confined condition. We try to maintain the displacement field to be 0. So here is the point that we park the gating or doping density of the sample, and then we measure the transport property across the wire. So for measuring across the wire, there are some contact issue which we try to avoid in the system. So with this, we can literally measure the transport property across the wire, across the structure, rather than measuring the contact effect, as was well known in 1D structures. And so what we observe is that with the temperature dependence, we observing the power law behavior. So which is very rare in a two-dimensional system. You can see that the resistivity or the conductivity or conductance, when it goes down, it follows a power law for two. And you can see this power law can be extended to, over 1 decade of the temperature ranges. And we can also perform the external bias dependence. So with the external bias, you can see the differential conductance, it shows the power law at the very high bias. So which is mimicking the behavior people have been observed in the carbon nanotube systems. So it follows both as a power law. So you can also see that the power law for the device here, which on the temperature power law about around 1. We also put the power law around 1 here as well. So it follows very well in the height bias with the external bias. So this mimics the one-dimensional Latin liquid behavior, but we observe such a behavior in a two-dimensional situation. So it gives you a single alpha and has the power law conductance along the hard directions. And another other possibility has been proposed during my talks at other places. So I want to highlight that this is exactly the power law behavior. We also plot the conductivity as the Arrhenius plot, which is the 1/t behavior, 1/t, as well as you might argue that it might be a variable Hawking situation. So it doesn't fit for both situations, either Arrhenius or a variable range Hawking situation. This is just barely because at low temperature range, it doesn't fit with the single one linear line behavior. But in the power law, you can see that at the low temperature range, it fits very well with the linear behavior in such a dual log plot. So this actually excludes the Arrhenius activation as well as variable range Hawkings. So there were also other proposals arguing that in such a COSY 1D structure, if you have some sort of amount of disorders, it could also create the so-called apparent power law behavior. But for this kind of people actually were proposing that the power law scaling parameter for the temperature and the external bias should be different. But in our case, we are seeing mostly the power law is equal from the external bias as well as the external temperature. So in our system, it's very unlikely coming from the disorder of the systems. So if we push further and then we tune the density, so you can suppose that the displacement field is 0. And then you can see the power law behavior as well as the anisotropy. The gray line as a background is the anisotropy of the system, and then the red, the transition of the dots here from the red to the blue is the numbers that we extract for the power law number of the system. So the extraction of the power law were all done by getting the temperature dependence at low temperature. And as you can see, in the whole doping region, starting from the charge neutrality, the power law is around 1, which is giving you a very strong of the system. As long as you dope the density to the system, and then the anisotropy drops together with the power law drops. So I want to note that at the very low power law number, which actually means that the resistivity or conductivity change at a very small number. Anything can be fitted in a power law. But this is not the case that you still have the Latinger liquid. It's just an indication that the parameter would have a significant change from some numbers. So we can reproduce this system, this observation in 2 systems. So which is one of the twist angle is 5 degrees and is on a twist angle of 6 degrees. We can use this in many systems. And move further, then you can see beyond this power law, very well fitted power law region, there is another region which has the resistance have a very little change. And you can see that it's almost barely not changing with the temperature dependence. And also the fitting here also at a very high doping density, very high electron dopings. So we should suggest that to see such a power law behavior, as long as the scaling, you should park the gate in the whole doping region of such a. And so to answer the question which I earlier posed here, can the Latinger liquid behavior be stabilized in 2 dimensions? The answer is yes. The Latinger liquid could be survived in such a system down to 1.8 Kelvin, and which can be discovered by can be captured by the strong anisotropy Latinger liquid behavior, which is the power law, as well as the tunable interaction and tunable channel distance. And the next question that I want to ask is whether we can have such a Latinger liquid behavior stabilized down to the lowest achievable temperature in our environment. And so, excuse me. So the answer that I want to give you is yes. We have pushed down to 50 millikelvin electron temperature, which is the reliable temperature that we can believe in the lab. And down Kelvin, we can still see such a good scaling of the power law with the tunable interactions with a huge amount of variable temperature ranges. And this was done in 3 degree devices. And you can moreover see if we measure the transport across the wire and also along the wire, the behavior with the external activation is completely different. So you can see that in the high anisotropy region, then the external bias, if we don't plot them as a log, but we plot them as a linear scale, you are seeing that the resistivity or the external, the differential resistivity will drop significantly with the external bias. But with the external bias along the so-called easy direction or along the COSY1D structure direction, you are seeing such a superconductivity-like behavior. So which means that sometimes when you are seeing the superconductivity like differential conductance, it might not be superconductivity. It could also be a collective behavior of a strong correlated system. So you can see that this is very similar to the superconductivity behavior, and it's an indication of a strong collective excitation of such a COSY1D systems. And also, as you can see, the anisotropy in the system. And if you further explore the system, so you can see the system can be categorized by a few different regions, which we call them as a phase diagram. So in the near the charge neutrality, up to a very high temperature, you can see the highly anisotropy Latinger liquid behavior. But as long as you dope the system to the very high isotropic highly electron doping, you can see the isotropic magnetic behavior. And along the whole doping at a very low temperature range, you can see the deviation of the Latinger liquid along the whole doping side. So we basic I point and H point here. So you can see that the power law start to deviate at a very low temperature, which might be entering into another new context, which haven't been explored yet. So to give you a quick summary, so we observe two-dimensional anisotropic Latinger liquid behavior or two-dimensional electronic phase, and it can be captured observe a nonlinear differential resistance along the EZ direction with a vanishing zero bias dips. And so this is a strong correlation which we in such a 2D anisotropic. And is there any connection to the early theoretical proposal of a sliding Latinger liquids? This remains a question. And so to move forward, what we should do is to investigate such a system as a direct probe of a of a spin charge separation. So if the Latinger liquid is the nature of such a two-dimensional anisotropic systems. And another possibility that we can explore in such a system is explore them up to a very high magnetic field. So which you can see the COSY 1D structures here. And they, if you apply a magnetic field, effectively we can shift the band structure along the momentum space. And then if you somehow can create interaction between the bands, and then you can open up a gap. And in this way, you might create a Landau level in a non-Fermi liquid. There has been numbers of theoretical proposals, but hasn't been realized experimentally. So I want to show you some preliminary results that we have got at the MAGLab. So if you fabricate the devices into a similar structure geometry, but we put a 4-probe measurements, and then with the twisting devices, if you apply a very high magnetic field up to 25 or even up to around like 45 Tesla. So what you can see is that we can see such a numbers of oscillating wiggles. And these oscillating wiggles can also be done by Fourier transform, and you can reveal some periodic structures here. And we are still analyzing all these data and also pushing the fabrication of the devices to higher qualities. And this is very promising that we could be possible to observe the quantum Hall effect in such a COSY 1D systems. And the main difference of such a system is that the starting point is rather a Fermi liquid, is a non-Fermi liquid system. And starting with a non-Fermi liquid system, with applying a magnetic field, we can see the Landau levels in the system. So is this any connections with the unconventional quantum oscillations in insulator, or is this coming out from some trivial contribution or trivial explanation that can explain such observations? And this remain questions. So in the future, we are pushing extremely hard in fabricating a very high quality air sensitive materials, so such as this twisted tungsten ditelluride, as well as other air sensitive materials. And can we see the fractional quantum anomalous Hall effects in such a system, or even a quantum Hall effect, or even fractional quantum Hall effect in such a system? This is the direction that we are pushing for. So this work has been mainly done during my postdoc in Professor Stephen Wu's lab in Princeton, and the major collaboration with was done with the graduate student who is now a Harvard Quantum Initiative Fellow in Harvard, Guo Yu, and as well as all the collaborators in Princeton. And I would also like to acknowledge my PhD research group, Xilin's lab in ICQM Peking University. And so as well as we are developing and pushing this twisted tungsten ditelluride system in University of Illinois to understand their strongly correlated quantum phenomena in my group in UIUC. So I want to give you a quick overview at the end. And so as you can see that all the graphene system has been discovered for around 20 years. And so till now, you can see that numbers of strong correlated system has been discovered. And so numbers of single layer system has been discovered. And seeing the trend, you can see that the samples is actually gradually getting more air sensitive. So we really need to find a way to push extremely hard to explore the systems which are air sensitive. So we are developing the techniques that we can fully do the operation and fabrication of the material inside a glow box or even at a very high vacuum. And with this direction, we might possibly observing the quantum systems in a very high, strongly correlated region. So this is the overview of my talk, and I'd like to take any questions.
All right. Questions?
Hi, this is Andre. So, great talk. So I wanted to ask about the effect of the twisting on this WT2. So basically, these are kind of large angle twists, right?
Sorry,
these are large angle twists.
Yes,
right?
This is relatively large angle.
And you basically don't really know very much about the single electron bands, right, in this system? Or do you? Is there any STM or anything that can tell us about the single electron bands? If the structure looks one-dimensional by lattice structure, that doesn't guarantee you at all one-dimensional electronic channels or vice versa. So is there some spectroscopic signature of how these bands look and what the Moire does to them?
Yes, that's a great question. So so we had to try to push along this direction, but the spectroscopy measurement so far has been extremely limited, especially in this twisted tungsten deuterium system. The main reason is because this material is extremely air sensitive. So to fabricate it, you have to capsulize this material with the hexagonal nitride, which is extremely limited for the STM study. And so what I want to also note here is that we actually has been developing some spectroscopy method in collaboration with Oak Ridge National Lab. So we are trying to fabricate these devices to be encapsulated with simple nitride. And with this method, if we can shine the light into the system, and then we can study their high energy spectrum, and we'll be able to understand excitation or excitons coming from the system. And with this, we could have some interpretation of how the single electron band or how the correlated band forms in such a system.
So, why if you just put one layer of HBN or whatever you would put on top of it and tunnel through it, that's still air sensitive, or why doesn't? Because the problem is this is a very complicated, even single layer system. So then when you twist it, you basically, there's no theoretical guidance, zero, right? It's very complicated. So oh, it's just terrible. It's not only that it's terrible, but the single layer structure is very complicated. So then when you twist, it's going to be even more complicated. Nothing can be done theoretically.
Yeah. So yeah, exactly. So the hardest thing is, as you can see here in the crystal, for example, in chromium triiodide, you can see that even after 2 minutes, the sample will get oxide. And then if you cover a simple nitride with the chromium triiodide, you're still getting it oxide very easily in 2 minutes. And for tungsten deuteride, it's very similar case, that if you cover a simple nitride, and then when you are trying to transfer from the glow box to your measurement system, you need really to hurry up. And especially for STM study, people need to bake to apply high temperature to the sample. It's extremely hard to explore such a system. So that's why I was proposing that we want to have a way to transfer and to load the sample with the experimental setup that can be completely compatible without any water. So if we have a way to transfer the devices or transfer the samples within different experimental without exposing it to air, and then we might have the possibility to explore the spectroscopy of such a material. So this is one of the directions that I'm pushing forward in my lab at UIUC.
Okay, any other questions? If not, let's thank Pengjie again.
Thank you.